Hi, welcome to another session of Mastering Google Cloud. Today's session is on Google Kubernetes Engine. I've been working on this session for some time, and just Kubernetes is such a vast concept, vast topic. Uh, to put all the concepts in the time frame of 25 to 30 minutes, it's a little challenging. But I've tried to cover up as much as possible all the concepts in depth in this session so that it will be very helpful for you in your exam, in your certification exam, or in your Kubernetes knowledge. So let's start working on Google Kubernetes Engine. So far, we have discussed Compute Engine, which is GCP's infrastructure as a service, which lets you run virtual machine in the cloud and gives you persistent storage and networking for them. And App Engine, which is one of the GCP's platform as a service offering. Now we are introducing you to a service called Kubernetes Engine. Kubernetes Engine is a managed environment for deploying, managing containerized applications. The cluster is made up of Compute Engine instances or instance groups and have no dependency on operating system. Kubernetes makes it easy to orchestrate many containers on many hosts, scale them, roll out new versions of them, and even roll back to the older version if things go wrong. It's an open source orchestrator for containers so that you can better manage and scale your applications. Some of the key features are it provides containerized infrastructure, supports automatic scaling, provides consistency across development, test, and production environment. It supports loosely coupled infrastructure where each component can act as a separate unit. One of the key components of Kubernetes is it can run applications on clusters of physical and virtual machines. And also it has capability to run the application on the cloud. Let's look into GKE architecture. It is a cluster architecture with master component and worker nodes. A cluster can have one or a set of master components. Worker nodes or nodes represent a virtual machine on Compute Engine. It contains pods, which is a scheduling unit. A pod contains one or more containers where your application runs. It's designed to run microservices. Master component is responsible for managing whole cluster. It manages health check of nodes, moves workload from field node to healthy worker node, and responsible for scheduling, provisioning, and exposing APIs to client. So what is a cluster? A cluster is the foundation of GKE. It's a set of master components that control the system as a whole and set of nodes, which are worker machines that run your containerized applications in containers. Kubernetes cluster runs all of the Kubernetes control plane components inside of a Google managed virtual machine instance. There are two types of clusters, zonal and regional. A single zone cluster has a single control plane running in one zone. This control plane manages workload on nodes running in the same zone. A multi-zonal cluster has a single replica of the control plane running in a single zone and has nodes running on multiple zones. If you want to maintain availability and number of your nodes and node pools are changing frequently, consider using regional cluster. A regional cluster has multiple replicas of the control plane running in multiple zones within a given region. Regional clusters are better suited for high availability. They have multiple master nodes across multiple compute zones in the region, while zonal clusters have one master node in a single compute zone. If a zonal cluster is upgraded, the single master VM experiences downtime during which the Kubernetes API is not available until the upgrade is complete. In the regional clusters, the control plane remains available during clusters maintenance, like rotating IPs, upgrading master VMs, or resizing clusters or node pools. When upgrading a regional cluster, 2 out of 3 master VMs are always running during the rolling upgrade so that Kubernetes API is still available. Use zonal cluster to create or upgrade clusters rapidly when availability is less of a concern. Use regional cluster when availability is more important than flexibility. Carefully select the cluster type when you create a cluster because you cannot change it after the cluster is created. Regardless of how you manage your cluster's version, it is recommended that you always enable auto upgrade for the cluster and its nodes. Release channel provide Google Kubernetes Engine best practices for versioning and upgrading your GKE clusters. GKE automatically resizes clusters node pools based on the demand of your workload. When demand is high, cluster AutoScaler adds nodes to the node pool. When demand is low, cluster AutoScaler scales back down to the minimum size that you designate. This can increase the availability of your workloads when you need it while controlling the cost. You don't need to manually add or remove nodes or over-provision your node pools. Cluster AutoScaler works on a per node pool basis. When you configure a node pool with the cluster AutoScaler, you specify a minimum and maximum size of the node pool. You can use gcloud command with enable autoscaling flag and specify min and max nodes. Cluster AutoScaler increases or decreases the size of the node pool automatically based on the resources request of the pods running on that node pool nodes. It periodically checks the status of pod and nodes and take the action. If pods are unschedulable because there are not enough nodes in the node pool, cluster AutoScaler adds nodes up to the maximum size of the node pool. If the nodes are underutilized and all the pods could be scheduled even with the fewer nodes in the node pool, cluster AutoScaler removes nodes down to the minimum size of the node pool. Do not enable Compute Engine autoscaling for managed instance groups for your cluster nodes, and this tip is very important for your exam question. By default, a cluster is created in a single zone and control plane, and nodes run all in the single compute zone. However, regional clusters increase the availability of both the cluster's control plane, which is the master, and its node by replicating them across multiple zones of the region. If one of the more, but not all, zones in the region experiences an outage, the cluster's control plane remains accessible as long as one replica of the control plane remains available. During the cluster maintenance, such as cluster upgrade, only one replica of the control plane is available at the time, and the cluster is still operational. By default, control plane and each node pool is replicated across 3 zones of the region, but you can customize the number of replicas. You cannot modify whether the cluster is zonal or multi-zonal or regional after creating the cluster. Nodes and node pool. A node is a worker machine that run your containerized applications and other workloads. Node pool is a group of nodes within the cluster that all have the same configuration. These nodes are individual machines or Compute Engine VM instances that GKE creates on your behalf when you create a cluster. These are workhorses of a Kubernetes cluster. Kubernetes let you deploy the containers on a set of nodes called a cluster. It's a foundation of GKE. It consists of at least one master and multiple nodes. A node runs the service necessary to support the Docker containers that make up of your cluster's workload. Each node is of the standard Compute Engine machine type. The default is E2 medium. You can select a different machine type when you create a cluster. When you create a cluster or a node pool, you can specify baseline minimum CPU platform for its nodes. You can create, upgrade, and delete node pools individually without affecting the whole cluster using the gcloud container node pool command. Pods. A pod is the smallest deployment unit in Kubernetes that you create or deploy. A pod represents a running process on your cluster as either a component of your application or an entire application. Think of pod as if you were running a process on your cluster. It's common to have only one container per pod, but if you have multiple containers with a hard dependency, you can package them into one single pod. The pod provides a unique network IP and a set of ports for your containers and options that govern how containers should run. They'll automatically share networking and they can have disk storage volumes in common. Each pod in Kubernetes gets a unique IP address and set of ports for your containers. Containers inside the pod can communicate with each other using localhost and ports that remain fixed as they are started and stopped on different nodes. One way to run a container on a pod in Kubernetes is using kubectl run command. Pods also contain shared networking and storage resources for their containers. Pods are automatically assigned unique IP address and they share the same network namespace including IP address and networking ports. Containers in the pod communicate with each other inside the pod on localhost. and they can specify a set of shared storage volumes that can be shared among the containers. Pod's lifecycle has following phases. Pending. Pod has been created and accepted by a cluster, but one or more of its containers are not running. This phase includes time spent on scheduling on a node or downloading images. Running. Pod have been bound to a node and all the containers have been created. At least one container is either running or in the process of starting or is restarting. Succeeded. All containers in the pod have terminated successfully. Terminated pods do not restart. Failed. All containers in the pod have been terminated and at least one container has terminated in failure. A failure container exits with a non-zero status. And unknown. The state of the pod cannot be determined. Because pods are ephemeral, it is not necessary to create pod directly. Instead, you can use a controller such as deployment, which creates and manages pods for you. Controllers are also useful for rolling out updates such as changes of a version of an application running in a container because the controller manages the whole update process for you. So let's discuss node components. There are two node components, kubeproxy and kubelet. Kubernetes manages connectivity among pods and services using the kubeproxy component. It is deployed as a static pod on each node by default. It helps in forwarding the request to a correct container and is capable of performing primitive load balancing. It makes sure that the networking environment is predictable and accessible at the same time it is isolated as well. It manages pods on node, volume, secrets, create new containers, health checkups, etc. It's an egress-based load balancing controller that watches the Kubernetes API server and continuously maps to the cluster IP to healthy pods based on the IP table rules. Kubelet is a small service that communicates with the master and it's responsible for starting and running the Docker containers scheduled on that node. It interacts with the etcd store to read configuration details. The kubelet process is responsible for maintaining the state of work and the node server. It manages networking rules, port forwarding, etc. Master or control plane has four components: API server, etcd, controller manager, and scheduler. Let's look into API server. The API server is a component of the Kubernetes control plane that exposes the Kubernetes API. It provides all of the operation on the cluster using the API. The API server is the front end for the Kubernetes control plane. It is designed to scale horizontally, that is, it scales by deploying more instances. etcd. It is a high availability key value store for all cluster data that can be distributed among multiple nodes. It stores the configuration information which can be used by each of the nodes in the cluster. It is accessible only by Kubernetes API server as it may have some sensitive information. Controller manager. Controller manager is a daemon which runs in non-terminating loop and is responsible for collecting and sending information to API server. It works towards getting the shared state of the cluster and then make changes to bring the current state of the server to the desired state. The key controller are replication controller, endpoint controller, namespace controller, and service account controller. The controller manager runs different kinds of controllers to handle nodes, endpoints, etc. Scheduler. This is one of the key components of the Kubernetes master. It is a service in master responsible for distributing the workload. It is responsible for tracking utilization on cluster nodes. In other words, this is the mechanism responsible for allocating pods to available nodes. Autoscaling in GKE. GKE resize clusters node pools based on the demand of your workload. When demand is high, clusters autoscaler add nodes to the node pool. When demand is low, clusters autoscaler scales back down to the minimum size that you designate. Clusters autoscaler automatically resizes the number of nodes in a given node pool based on your workload. You don't need to manually add or remove nodes or over provision your node pools. Instead, you specify a minimum and maximum size for your node pool, and rest is automatic. Important point to note, do not enable Compute Engine autoscaling for managed instance groups for your cluster nodes. GKE's cluster AutoScaler is separate from Compute Engine autoscaling. If your node pool contains multiple managed instance groups with the same instance type, cluster AutoScaler attempt uniformity or consistency in the sizes of these managed instance groups when scaling up. This will help prevent an uneven distribution of nodes among managed instance groups in multiple zones of a node pool. However, AutoScaler can scale down unevenly across zones. Scaling an application. When you deploy an application in GKE, you define how many replicas of the application you would like to run. When you scale an application, you increase or decrease the number of replicas. The kubectl scale method is the fastest way to scale. You can autoscale deployments based on CPU utilization of the pods using kubectl autoscale. When you use kubectl autoscale, you specify a maximum and a minimum number of replicas for your application as well as CPU utilization target. kubectl autoscale creates a horizontal pod autoscaler or HPA object that targets a specified resource called the scale target and scales it as needed. Rolling updates. You can perform a rolling update to update the images, configuration, labels, annotations, and resource limits and requests of the workloads in your clusters. Rolling updates incrementally replaces your resources pod with new one, which are then scheduled on nodes with available resources. Rolling updates are designed to update your workload without downtime. You can use kubectl rollout to inspect a rollout as it occurs, to pause and to resume a rollout, to roll back an update, and to view an object's rollout history. Deployments. Deployments represent a set of multiple identical pods with no unique identities. A deployment runs multiple replicas of your application and automatically replaces any instances that fail or become unresponsive. You can create a deployment using a kubectl run, kubectl apply, or kubectl create commands. Deployments are well suited for stateless application and stateful applications. The common management tasks for deployments are inspect, scale a deployment, autoscale using horizontal pod autoscale, and delete. Deployments can be in one of the three states using its life cycle: progressing, completed, or failed. A progressing state indicates that the deployment is in progress of performing its tasks. A completed state indicates the deployment has successfully completed its tasks. A failed state indicates the deployment has encountered one or more issues that prevent it from completing its tasks. To scale a deployment, run a kubectl scale command. Service in GKE. A service is to group a set of pod endpoints into a single resource. A service identifies its member pods with selector. In a Kubernetes cluster, each pod has an internal IP address, but the pod and deployment come and go, and their IP addresses changes, so it doesn't make sense to use pod IP address directly. With the service, you get a stable IP address that lasts for the life of the service. Type of services are cluster IP, node port, load balancer, external name, and headless. And we will discuss load balancing service. When you create a service of a type load balancer, the Google Cloud Controller configures a network load balancer in your project. The load balancer has a stable IP address that is accessible from outside of your project. It supports L4 load balancer. To deploy and manage your containerized applications and other workloads on your GKE cluster, you create a Kubernetes controller objects. These controller objects represent the applications, daemons, and batch jobs running on your clusters. You can create these controller objects using the Kubernetes API or by kubectl command line interface. Networking in GKE. The Kubernetes networking model relies heavily on IP addresses. Services, pods, containers, and nodes communicate using IP addresses and ports. Kubernetes provide different type of load balancing to direct traffic to the correct pods. Cluster IP. The IP address assigned to a service. This address is stable for the lifetime of the service. Pod IP, the IP address assigned to a given pod. This is ephemeral, as discussed in the pod section. Node IP, this IP address assigned to a given node. Let's look into networking inside the cluster. Each node has an IP address assigned from the cluster's virtual private cloud (VPC) network. This node IP provides connectivity from control components like kubeproxy and kubelet to the Kubernetes API server. This API is the node's connection to the rest of the cluster. Each node has a pool of IP addresses that GKE assigns pods running on that node. You can run a maximum of 110 pods on a node with the /24 CIDR range. Each pod has a single IP address assigned from the pod CIDR range of its node. This IP address is shared by all containers running within the pod and connects them to the other pods running in the cluster. Each service has an IP address called the cluster IP, assigned from the cluster's VPC network, and you can optionally customize the VPC network when you create the cluster. Now let's look into networking outside the cluster. GKE provides 3 different types of load balancers to control access and to spread incoming traffic across your cluster as evenly as possible. You can configure one service to use multiple types of load balancers simultaneously. External load balancer manages traffic coming from outside the cluster and outside your VPC network. They use forwarding rules associated with the Google Cloud Network to route traffic to the Kubernetes nodes. Internal load balancer manages traffic coming from within the same VPC network. Like external load balancer, they use forwarding rules associated with the Google Cloud Network to route the traffic to a Kubernetes nodes. HTTPS load balancer are specialized external load balancers used for HTTPS traffic. They use an ingress resource rather than a forwarding rule to route traffic to a Kubernetes node. This ends our session on conceptual understanding of Google Kubernetes Engine for your certification and for your day-to-day work. Now we have some problems which are important for your certification exam. So let's go over these problems and try to solve them. You have an application deployed on Kubernetes Engine using a deployment named eco deployment. The deployment is exposed using the service called eco service. You need to perform an update to the application with minimum downtime to the application. What should you do? You have 4 choices. And the last 2 choices are using the YAML file, which in my opinion is not the right choice. The first 2 choices are using the kubectl set image deployment command, and the second choice is use the rolling update functionality. As we have discussed, you can perform a rolling update to update the images, configuration, labels, annotations, and resources limits and requests of the workloads in your clusters. Rolling updates incrementally replaces your resources pods with new one, which are then scheduled on nodes with available resources. So rolling update is the mechanism, is the mean, is the concept, but the command is kubectl set image deployment echo deployment new image. So option A is the right choice. This problem says your company is migrating its on-premise data center into the cloud. As a part of migration, you want to integrate Kubernetes Engine for workload orchestration. Parts of your architecture must also be a PCI DSS compliant, which of the following is the most accurate. Now we have not covered PCI DSS compliant up till now, but we understand that that is an important feature in Google Cloud to have that compliance. All the resources should be compliant with PCI DSS. So again, you have 4 choices here. App Engine is the only compute platform that is certified for PCI DSS hosting, which is not true. Kubernetes Engine cannot be used under PCI DSS, which is not true. And option D, all Google Cloud services are usable because Google Cloud Platform is certified PCI compliant, which is also not true. So this option C says Kubernetes Engine and GCP provides the tools you need to build the PCI DSS compliant environment. So it is the responsibility of the application and the application owner to build the application which is PCI DSS compliant, and GCP and Kubernetes Engine provide the tools to do that. So option C is the right choice. So option C is the right choice. Kubernetes Engine and GCP provide the tools that you need to build the PCI DSS compliant environment. In this question, the development team has provided you with the Kubernetes deployment file. You have no infrastructure yet and need to deploy the application. What should you do? You have four choices. In the first choice, use gcloud to create Kubernetes cluster and deployment manager to create the deployment. In option B, you use the gcloud to create Kubernetes cluster and use kubectl to create the deployment. We have just read that we use gcloud to create the Kubernetes cluster and kubectl to create the deployment, and B looks like the right choice. Option C, use kubectl to create the Kubernetes cluster. It's not right. And option D, use kubectl to create the cluster. Again, it's not the right choice. So option B seems to be the right choice. So option B, using gcloud to create the Kubernetes cluster and kubectl command to create the deployment is the right choice. In this one, you want to enable your running Google Kubernetes Engine cluster to scale as demand for your application changes. What should you do? You have four options here. In the first two options, you are adding either a node or a tag to instance, which is not the right choice. Option D, create a new Kubernetes Engine cluster with the following command. That is also not right choice because you are just trying to scale it up. So option C, update the existing Kubernetes cluster with the following command, and you update the cluster using enable autoscaling, minimum nodes, and maximum nodes. And we discussed this in our previous scaling section. So we should use enable autoscaling for an existing node pool. We should use gcloud containers clusters update command. And here's the link. I will post this link in the comment section, and then you can use this link to check the command. In this problem, you want your Google Kubernetes Engine cluster to automatically add or remove nodes based on CPU load. So we have covered that how we use horizontal pod AutoScaler with the target CPU usage, and we have the GCP console where we can do that. So let's look into that. So we have already covered that pods are created on new nodes when horizontal pod autoscaling is enabled. So we can use the console to autoscale the deployment based on CPU utilization of pods using kubectl AutoScale or from the console. So option A is the right choice. Configure a horizontal pod AutoScaler with the target CPU usage. Enable the cloud AutoScaler from the GCP console. In this problem, a development team at your company has created the Dockerized HTTPS web application. You need to deploy the application on Google Kubernetes Engine and make sure that application scales automatically. So this refers to the section networking and scaling of application. And option A, which seems to be the right choice, use the horizontal pod AutoScaler and enable cluster autoscaling. Use an ingress resource to load balance the HTTPS traffic. Please refer to networking section where we have different type of load balancing services and how we use ingress resources to load balance the HTTPS traffic. So when you create a service of type load balancer, GKE makes appropriate Google Cloud API call to create either an external network load balancer or internal TCP UDP load balancer. When you specify an ingress in the resource manifest, you instruct GKE to create an ingress resource. GKE makes appropriate Google Cloud API calls to create an external HTTPS load balancer. The load balancer URL map to one or more backend services where each backend service is referenced in an ingress. If you are exposing an HTTPS service hosted on GKE, HTTPS load balancing is the recommended method of load balancing. So option A is the right choice. This ends the session on GKE. As I mentioned earlier, Kubernetes is a vast topic, a little challenging to complete in 30-35 minutes, but I tried to cover up almost all the concepts that are required for your certification exam. So you can go deeper in autoscaling, scaling the application, networking, load balancing, architecture components. They are all covered in detail in the documentation of GCP. Your suggestions are very welcome. Your comments, definitely please put your comments so that I can review and we can go ahead with different sessions. So till then, thanks a lot and happy GCP learning.